Welcome to KCC Diesel Online. My name is Jeff Rush, and this is DST 110H electrical components. So today we'll be covering electrical components. Our learning objectives for this lesson are going to be learning to use a voltmeter, if a switch is opened, closed, or defective, define the function of each terminal of an ISO standard relay, troubleshoot a circuit controlled by a relay, and list the most likely failures of a relay, explain how the circuit protection devices, or CPDs, operate, and the importance of replacing CPD with the proper rated and specified for the OEM. Using a voltmeter to determine if a CPD, or a circuit protection device, is open. Locate a open circuit and a shorted to ground circuit using wiring schematics and electrical test tools. A wiring harness is a modularized section of wires designed to be connected to the electrical components and other wiring harnesses. Now, one of the major functions over the years of a wiring harness has been to make the vehicle so that it can be assembled. So a lot of the functions of the modern wiring harness that you're going to see are functions for assembly, not functions for proper operation of the vehicle. And over time, you'll find out that the wiring harness may need to be modified such that we're taking out the features of assembly. So if there was a connector in a place that got road salt in it, and instead of replacing that connector, replacing one end and the other end so that they connect, what we'll actually do is just remove it and then splice the wires together properly, assuming that the vehicle will never have to be disassembled in that way ever again, that was really just for one-time only assembly, but that becomes a chink in the vehicle's harness, a weak point. So we want to remove those weak points sometimes. So we have connectors that are the interlocking devices that permit connections to the electrical components. We have terminals. They are the electrically conductive pins, the male and female sockets, that provide electrical connections between connectors. All right, so here's a picture of a standard wiring harness. And this connection here, this is going to be, like at your bulkhead, at the firewall of the vehicle. And, everything on this side is going to be engine, and everything on the other side is going to be body or cab. And, really these functions are very important, but when you get into these big pin connectors, obviously a lot of different connections are going through there. So we have to learn how to read the schematics so that we understand which pins are in these connections. All right, so here's a tech tip. You may find one or more terminals that may be missing in a multi-terminal connector that has been exposed to road salt mixed with water, while another terminal may only have a small amount of corrosion. The terminal in the connector supplied with constant battery power or high current can dissolve in a brief amount of time when exposed to salt water. This is more of an East Coast problem where they salt the roads, but the chemical de-icers are just marginally better. It's a pretty small margin. They're still destructive. So, if you're running salted roads or if you're running de-iced roads, this type of damage can happen. That's why making sure that the seals, the weather pack seals and things like that on your connectors are in place and sealing properly. The use of like dielectric grease and things like that really helps long term to minimize the damage of salt or de-icer. All right, wire details. So wire is, most of our wire in our automotive vehicles is stranded wire versus like the solid wire you would see in a house. Wire made up of several smaller diameter wires, and the most commonly found in trucks. Okay, wire diameter is most commonly measured by the American Wire Gauge, or AWG, or the International Organization's Standardization, the ISO. And so both of these are organizations that are standardizing our wire size so that we know what size wire we're working with, what size wire, what size terminal we need to repair it, things like that. So the wire size is the actual conductor. I'm sorry, the wire size is the actual conductor, not the insulator. So it's tough sometimes because you'll see wire that's like really premium. It'll have a rubber coating. It'll be a lot thicker than maybe some of the plastic vinyl style coverings or coatings on the wire. So the insulator on the outside of the wire can be constructed of different material. Usually we see that our wire is printed with the actual conductor's size on the outside of the wire, and that can help for when we're trying to strip the wire, peel back the coating on the wire for repairs, things like that. So that's helpful. All right, so here's that stranded wire. So here we have our insulation on the outside, and on the inside we have our copper. So this copper on the inside, that's our actual conductor. All right, there we are. We're back. Sorry about that. All right, so the stranded wire is our regular wire. The smaller the AUG number, the smaller AWG number gets, the larger the wire diameter gets. So the smaller the AWG number gets, the larger the number. So a number 1 would be very large in comparison to a number 22, which would be very small. So it's a little little less intuitive. We kind of think of larger numbers being larger sizes, kind of like your foot size or whatever. But with wires, the smaller the number, the bigger the wire or cable. The larger the number, the smaller the cable. Cable is often used to describe large diameter wires. So when we get up to double-aught cable, that's our battery cables. 3-aught cable, that's our battery cables. So once we start to get to those smaller numbers like 1, 2, 3, that ends up almost being a cable size wire. ISO metric wiring indicates the cross-sectional area of the wire in millimeters squared. The larger the ISO rating, the larger the wire diameter. So that's more intuitive. Obviously, you think about foot sizes, you think about things like that. So the larger the ISO rating, the larger the wire diameter. And that's just backwards. So we Americans like to do things backwards every once in a while. So here you can see that indicated in the wire sizes. So a 0.5 millimeter wire would be equivalent to a 20 gauge wire, and it would have a 4 ampere capacity. And then as we get up to the 25 millimeter wire, we get to a 4 AUG size wire, and that can take 60 amps capacity. So the metric, the higher the number goes, the higher the ampere capacity, which is helpful, right? They're directly proportional, and it's just absolutely the opposite with American wire gauge or AWG. So you'll have to remember that. That takes a little bit of a learning curve. Wire details. So the resistance of a wire decreases as the diameter increases. So the bigger the wire, the less resistance. The resistance of a wire increases as the length of the wire increases. So the resistance of a wire increases as the length of the wire increases. So the longer the wire, the more resistance. So if you want to go a larger distance with your wire, you may need to go up in size to compensate. That's the application for these two rules, basically. Because wire resistance increases with length, it may be necessary to increase the wire gauge for loads that are long distance for the voltage from the for the voltage or from the voltage source. Automobiles often use polyvinyl chloride material as an insulator. So it's that plastic kind of rubbery material. Most insulators are color-coded to provide circuit identification on the vehicle. So I come from a Ford background, and Ford was great at this. It was, yellow and white, pink and blue, and when you see that wire put out there, the pink was the larger size, and the red or the blue was the tracer, the small wire. So the majority, like 90% of the wire would be, or the insulator would be pink, and 10% would be blue. And it was very easy to read. Now, as we go towards the ISO, this is where we lose some of that functionality. You'll have a whole group of wires be white, a whole group of wires be black. Not quite as easy to decode or discern which wire is which. So I really liked the Ford style. I hate to see them go away from that. On heavy trucks, we've never really adhered to that Ford style wiring. So you're going to see a lot of wires that are the same color, and then the vinyl printing on the outside of the wire will tell us the location and purpose of that wire. All right, most insulators are color-coded to provide circuit identification on the vehicle. Chassis ground. Current needs a path from the positive terminal of the battery through the electrical device and back to the negative terminal of the battery. The negative terminal of the battery is connected to the steel frame rails, providing the return path to ground. When the negative battery terminal is connected to the frame rail, it is said to have a negative ground. Okay? When the negative battery terminal is connected to the frame rail, it is said to have a negative ground. Okay? A negative ground system, only a positive wire is needed from the battery. And you're going to see some different styles of this, but when we call things chassis grounded, that's what we mean. It's grounded at the frame. This is most of our electrical systems in the automotive and diesel industry. All right, typical chassis ground symbols. So here's our chassis ground symbols. So we have our ground here with our, basically our upside down T with some descending lines like this. We may also see a triangle, and we may also see some sort of a antenna looking, kind of upside down antenna looking guy here. These are all ways that we can show things are grounded. So if we look here, we have our positive battery terminal. We come around, we go through our resistor, we go, follow our connector around, and we go to ground. Well, that's obviously a long, we're using a lot of wire here. We had to run all this wire to get the positive over here, but we had to run all this wire again. So that's a lot of wires going to and from the component. So what we will actually do is we will send our positive this way to the component, and then we will send our ground here, and we'll ground here. And so that imaginary ground connection between these two comes from the frame, the chassis itself. Could be the body of the vehicle, but we have to make sure that everything is grounded properly. All right, flexible conduit wire insulation protects from abrasion. So this conduit here, we call it split loom. It has several different names, but this is wrapped around our wiring harnesses to protect the wire from abrasion, chafing against one another, dirt, all sorts of things. Keeps the harness clean, keeps it from chafing, and it also covers the wire up. So when we are doing our diagnostics, oftentimes this can be covering a problem, and so you have to go searching inside this loom for the problem. All right, wire harness repairs. So standard compress or crimp style butt connectors are fast. However, there are different qualities, different types, and you need to use some workmanship and make some right choices when it comes to a crimp style butt connector. Heat shrinkable butt connectors are preferable. Okay, so we want the highest quality. Now they make butt connectors that heat shrink, and then they make butt connectors that heat shrink and have a weather pack seal, a glue that actually expresses as you heat it up. The hot glue inside this connector comes out and it kind of protrudes from the end of the the connector and actually seals it up from water and things like that. That's the preferable. Now, what you are going to find, you know, at Walmart, at Fred Meyer, even a lot of auto parts houses, are the cheap vinyl connectors. They crimp on. They have a cheap piece of vinyl on the end of it, blue, red, to indicate the sizes. But they don't heat shrink. They don't seal. I won't even use, I mean, if I use those, it's for like speaker wire in my house. I won't use them on a car. I won't use it on anything critical. You know, it's just not a professional grade terminal, and so we don't use them. Soldering wires and then covering with a heat shrinkable tubing is the preferred method for repairing if time allows. So oftentimes time and space are an issue. Getting up underneath the dash and being able to solder and then solder and heat shrink and do all that, you may not have that space. So sometimes space is also an issue, but time, you know, obviously it takes a lot more time to solder and then use a piece of heat shrink to cover over that solder. So we'll use some heat shrink butt connectors, high quality heat shrink butt connectors in those instances. Soldering wires and heat shrinking is preferable and pretty mandatory when it comes to electronic circuits. We're talking, you know, the circuits that are low voltage, low current signal circuits that don't need to be degraded by, you know, extra resistance because they are so low current already. So we really watch out for those electronic circuits. Plastic or electrician's tape is not acceptable for sealing wire repairs outside of the cab. So I try not to use electrician's tape to cover over a solder joint or anytime, like almost never. That's not a professional repair. They do make they make a paintable tape, a plastic or a liquid tape. I will use that in a pinch. I'm usually using it because I've made some sort of an error. I've soldered wires together and I forgot to put the heat shrink on, or I put the heat shrink on but I got it a little too hot and the heat shrink actually shrunk to the wire and now I can't slide it over my splice, and maybe I don't have time or space. Maybe I have too short of wires. I can't cut it all out and do it again. So there are some allowable deviations from the preferred practices. However, you know, we always want to try to do the most professional job. The big difference, and I'll preach this quite a bit, the big difference between auto electrical and diesel electrical. Diesel, everything you do in the diesel industry needs to go for 100,000 miles. It needs to be rock solid. It needs to be as perfect as can be. So we try to do the most professional job. So if I forgot to put my heat shrink on, or accidentally shrunk my heat shrink because I got my solder too hot, something to that effect, you know, I can use that liquid tape. However, that's not the best repair. So I would be tempted to go back, cut it out, do it right, get it done right. Crimp type butt connectors with heat shrinkable installation. So this is what we're looking at. So this is a brand name, Duraseal. Okay, it comes in 3 different sizes. Now, if they were showing these in color, this would be pink, the 18 to 22. This would be blue, and this would be yellow. So they go up in size as they go. So this is the 14 size here, you know, between the 18 and 22, and then between the 10 and 12. But as you see, the butt connectors get bigger as the number gets smaller. So that's that American wire gauge. Connector terminals, they're oftentimes molded connectors that contain terminals, molded in a rubber or soft plastic material. So you'll see both. Molded terminals are often designed to mate with a specific device or component. Hard shell connectors, which are, you know, are big connectors at the end of the wire, may contain 1 to 80 or more wires Hard shell connectors are used to provide interconnections between wiring harnesses and electronic modules, sometimes between the bulkhead and the engine, things like that. So here's a hard shell connector. So you see that this one's an 8-wire connection, and then we have one that's really large down here. And then as you look and as you're doing your reading, you're going to find out here on figure 412 that this is a weather pack seal. So as this wire slides into the back of this connector, it needs to be sealed from the elements. So we can have a big seal here at the back, or we can have each individual wire being sealed. Both are pretty good, but both can fail, and you can have road salt or de-icer or rust or corrosion get into that wire. So we want to be careful of that. All right, we have lots of different special crimping tools. So here we have the terminal crimping tool, and basically these little wings are going to crimp onto the wire and make that good electrical connection. And then we have the larger wings that are going to crimp onto the actual insulation of the wire. And these large wings might also be on the actual rubber weather pack seal. So here's a good example of that. This is crimped onto the wire and the seal are crimped onto the on the insulation. And then you see that this one's installed through the back of the connector. Then you have this style of connector here where the wire comes all the way through. Then we are putting the terminal on and then pulling the wire back into the connector. This style is good because if the wire gets pulled, it only gets pulled into the connector, versus if the top wire here gets pulled, it's going to pull out of the connector. So kind of a difference in durability and application. All right, so we're showing here in figure 420 that we're pulling this terminal back into position. That also means that terminal can't be pushed out for any reason. This style here, this is our Deutsch connector. All sorts of funny stories about Deutsch connectors. The Deutsch connector terminal tool will slide up the back of the wire, defeat the tangs, and then you'll be able to pull the wire out the back. And so we have lots of special tools for wiring terminals, and we put a lot of emphasis on education for wiring terminals. Switches. So our switches are really kind of our control devices in the circuits. So when a switch is on, it is closed. So wrap your head around this one for sure. When a switch is on, it is closed. When a switch is off, it is open. So we're closing that connection. So the switch is on, it's closed. Okay. When the switch is off, it's open. Okay. The two pieces of a switch that are actually make or break current are known as the contacts. Okay. Poles describe the number of input terminal and the number of an input terminals that the switch has. Throw describes the number of positions a switch can be moved to and still complete a circuit. So you may have an on, off, on, style. So one closed position is an on, and it does function A. Then we go to off, where no functions are happening, and then function 2, or the second function, or the B position would be yet another function that does something else. So we have a lot of wires, or a lot of switches that are like this, and we'll talk about more of those in lab. The two pieces of a switch that actually make or break, I'm sorry, I'm repeating myself there, sorry. The term pole and throw are used together to describe the basic functionality of a switch. So here's our switch open. So here's another good example with a knife style switch. Here it is open. Nothing can pass through this. So this is an open circuit. Okay. Here's the switch closed, and this is a closed circuit. So obviously we'd have to have a large amount of electricity to jump or arc between this switch and the open position. It'd have to be kilovolts and things like that, like a kind of like a spark plug. And then when it's closed in this position, obviously we have low resistance, we have good continuity, and our electricity is going to flow through there very easily. All right, so here's our switch types. So here we show a single pole, single throw. Okay, so we're only operating one thing, and we have an on and an off. Okay, and so we have an open and a closed switch. Now we come over here to the double pole, single throw, and same thing, except now we are controlling two circuits with one switch. And then down here we have a single pole double throw, and so we can be on in this position or we can be on in this position. It just depends on how we have that switch set. All right, switches. Latching switches remain in the position that they are placed in. So this is that push button that latches. Okay, so we push it and it clicks and it stays there. Momentary contact switches are those open and closed switches. One really good example of a momentary contact switch is your horn. Okay, so you hit that horn, and it blares until you let it go. So it's a momentary contact. As long as you're pushing on it, it makes contact. But the moment that you let off of it, it stops. The normal state of a momentary switch, the contact position when the switch is not activated, can be two different states. So you can have a normally closed switch or a normally open switch. So normally closed, the device would be, the current would be allowed to flow through that device all of the time until you push on it. Then you have normally closed, or no, I'm sorry, normally open, I apologize. Normally open would be like your horn circuit. Your horn circuit's normally open, so nothing can flow through it. It's open. And then when we push the button, it closes the circuit, and now we're able to hear the horn and put current down to the horn. All right, so here is our showing a multimeter on a circuit. Okay, so we are going to start to introduce some concepts here. I want you to look at this circuit. So we have our positive on this side, and we have positive voltage going here, and we're touching our voltmeter here. So we see that we have 12 volts showing. But in order for that 12 volts to be showing on the meter, we also have to have a ground. So the other leg of our meter, the other probe of our meter, is touching the ground side. So we're getting ground from the battery coming up through our resistor and back here. So with the switch open, no voltage is being used. So we are going to get our 12 volts. Okay, no voltage is being used. Down here across the resistor, we're going to have 0 volts. So what they're doing in this test right here, where they're testing right across to the switch here, or right across the load here, we're going to have 0 volts. Now that is a voltage drop test. Right now, when I put those two meters in that position, I am checking to see what is flowing across that load. And right now, because the switch is open, we don't have any voltage flowing, no current flowing, or no voltage at the component and no current flowing. We have 0 volts being used. So now we're going to close that switch, and we're going to see right here where we checked there, we have 0.1 volts there. So now this turned into a voltage drop test of itself. So right now, as the voltage flows across that switch, from here to here, we have 0.01 volts being used. That's a very low voltage drop, but it's still significant, because the sum of our voltage drops has to equal our source voltage. So in this case, our source voltage really does have to add up. So we lose 0.1 voltage right here. Okay, we come around, now we're doing a voltage drop across our load, and 11.99 volts are being used across our load. So if we had a 12 volt source like they're showing us here, 11.99 plus 0.01 volts equals our source voltage, and we can see that our switch is closed and everything's operating properly in this circuit. All right, so now we're going to troubleshoot a switch, and let me just throw this out there. If you're watching and you're not getting this, and this seems pretty foreign to you, and you're not wrapping your head around it, that is okay. Do not panic. We are going to taste this, touch this, smell this, watch it light up, make some sparks. You are going to get all the opportunities you need to kind of wrap your head around this. We are just introducing the concepts. Now, some people are going to read this and totally get it. And then they're going to go to lab and they're going to try to apply it, and maybe the hands-on portion they'll struggle with. Then there'll be others of you that will read this, not get it at all. We take you out there to lab and you try it and you totally get it. And then there'll be people who, they read it, they sort of get it, they do it in lab, they sort of get it, and it all adds up. And then there'll be yet another category where you'll understand through a couple of different methods, you'll understand 50 to 80% of what I'm teaching you today, and need to learn the rest of it later. Most people, even myself, when I learned automotive electrical, I needed time to solidify the concepts. I needed practice to solidify the concepts. So don't feel like you need to master this by watching a video. Don't feel like you need to master this by doing it the first time. We're going to do this repetitively. And remember, our class is secular, so we're going to keep coming back to things. I'm going to introduce the concept today. I'm going to introduce a couple more concepts, then I'm going to come back and tie it all together. And then we're going to introduce some more concepts, and then I'm going to come back and tie it together. So don't feel like if you miss it today, you're never going to get it. We're going to come back to it, okay? So let's look at this defective switch right here. So if we talked a little bit about voltage drops. Now, in the last slide, this 11.9 volts was 0.01 volts. And that was normal. That was normal. Well, what's our intended load in this circuit is this resistor. So if the sum of our voltage drops is supposed to equal our source voltage, and our intended load was this 1 ohm resistor, and this switch is just supposed to open and close that, it would be bad design if our switch took all the voltage and our intended load, this 1 ohm resistor, took 0.1 volts of current, or voltage. So this is bad. This shouldn't be that way. This is a very high resistance closed circuit. So then we're going to come over here to an open circuit. So here our open is right after the battery. So our open stops, right? Or our voltage stops flowing right here. So if we go and we look and we do that same test at the switch, where we should have 12 volts right here, we have 0 volts because our 12 volts is not getting to the switch. Where the closed switch should have been somewhere about 0.1 or 0.01 voltage drop, we're getting 0 again, and we're getting 0 volts drop across the load. So really, we know that the voltage, the problem in this circuit is from the switch back to the battery. And somewhere in that harness we have an open. So then we'll look here where our open is past the switch. And we can see that because when we use our voltmeter and we look here at the switch, we find that our switch right here, it's closed, and we're getting 12 volts across that switch at this point. Then we go to the next point in the circuit, and we have no voltage there. So all of our voltage is lost before we actually get to that point. Now I want you to note that between this meter, where both legs of the meter are in the circuit, parallel into the circuit, this one is going to the positive wire and then to ground. So we are just trying to see how much voltage is at this point, not actually what's being used or dropped. So that's significant. And we'll talk a lot about that when we go into lab. All right, so here's a relay. And our relays, we're going to hold these and touch these and get to check them out. But this is our little electromagnet. Okay, so this is that little electromagnet we were talking about. So we are going to put power to this electric magnet, and it is going to create, this electromagnet is going to create that magnetic field and suck this metal down onto these contacts, and that's going to close the circuit. So this is a switching component, okay? This is going to help us switch. The whole purpose in life of a relay is to control a large amount of current with a small amount of current. So I want you to think about our starter. Our starter is one of our larger electrical components in the car. It takes a tremendous amount of current and amperage to flow through that starter to get it to start. Now, we don't want that amazing amount of current to flow through our key switch. Our key switch is a tiny wire, right? Otherwise, we'd have to have a big old cable coming up to our key switch and a big old cable leaving our key switch, and our key switch would be huge. So instead, what we're doing is we're using a little wire connected to a relay to control a large amount of current elsewhere. And that's what is exactly what a relay does in a component or in the system. All right, so we'll talk about the terminal designation and function of an ISO or DIN relay, and we'll talk a little bit more about ISO and DIN as we continue through our wiring training. Pin 85 and 86 are the coil terminals. Are normally 50 ohms to 100 ohms of resistance between them. Okay, 30, the common terminal, normally connected to the power source. Okay, 87 is the normally open terminal. When the relay is energized, the 30 and 87 terminal will close. Okay, and then 87A is the normally closed terminal. When the relay is energized, 30 and 87 will be open. Okay. So here's what this looks like. So we kind of described that. So you may want to go back and have to do that reading again. To see what's going on there. So here's the bottom view of the relay, and they are normally marked just like this. Okay, so you've got your 30, your 85, your 86, your 87. Okay, so we'll talk a little bit about this. Okay, so we can make some assumptions because of the design of vehicles. They've tried to design them very similar so that things work out on a pretty regular basis. Okay, so 86 and 30, okay, tend to be our powers. Okay, this will be hot all the time. This 30, hot with the key on, or hot all the time. This 86 or 87 is going to be activated by some sort of a switch or a computer. Okay, and this 85 is going to be our ground. It's going to be grounded all the time. And 87A, okay, it's going to go out to whatever component. I'm sorry. Let me restate that. This 87A, when it's de-energized, may do nothing. It may also send a signal to a component to say, hey, this component's not on. But oftentimes this one is just blank. So we go over here to our 87. That is going to be our component that we are trying to power. That's going to be our intended output. Okay, so we get this input from 86. Okay, and we have our constant voltage here, just waiting for some work to be done for the circuit to close. So our 86 gets energized. It finds ground at 85. It creates the magnetic induction in here, and it closes the switch with the magnetic field and closes 87. And now our voltage from pin 30 here can flow out pin 87. And so, that's our horn circuit. That's, our starter circuit, our headlights, all sorts of things, blower motors, AC, all sorts of things run off the relay. Okay, so that is a brief explanation. We are going to go into this a whole bunch more when we go into lab. All right, here's another view of that typical relay. So now this is going to be the electrical schematic view. So when you go into an electrical schematic, you may see it look more like this. But still, all is the same, okay? We still have our terminals all doing the same thing, okay? So 87 and 30, or I'm sorry, 86 and 30 are still our powers, okay? 85 is still our ground, and these are still our outputs, okay? And you will see this as a pretty common theme, okay? So I'm not going to go over this a ton right this second because it's very complicated, and most of you may not be getting it right this second. You know, seeing it audio visual may not be your learning method. So I'm not going to beat this one to death, and I don't want to confuse you too much. But I do want to show you this. Okay, so now we've got our relays up here. Okay, and we've switched now from the ISO to the DIN European style, and so now our terminals have changed to 1, 2, 3, 4, and 5, and they're still doing the same functions, but you just have to figure out what's what. And you know what's going on where, you know, which one's our power, which one's our ground. But again, they're going to be very standardized over the design of the vehicle. All right, so here is a larger relay. This is going to be like our starter relay, and this is what we call a mag switch. This switch has a very large set of contacts in there. The contact disc is copper, it's large, it's going to make good contact, it's going to flow a lot of current. And these windings in here, those can be continuous windings to hold it on continuously. In the case of we're sending large amounts of power for a long period of time, or it could be momentary contact like a starter. Okay, so as long as we're in the starter switch position, those windings hold us in and keep the vehicle starting, or keep the starter turning, I should say. All right, circuit protection devices, or CPDs. These are our fuses, circuit breakers, fusible links, positive coefficient devices. So we have a lot of different styles of current protection devices. Current protection devices will allow current flow up to the current rating and then melt, open, and open the circuit. So that's a fusible style. OEMs select the current ratings based on the smallest wire in the circuit being protected. Okay, so obviously we designed to the weakest length, or link, I should say, weakest link. All right, so our weakest link will always be that smallest wire, so we designed for that. All right, circuit protection devices continued. Any additional wiring added to the truck should be protected by a circuit protection device. So let's say you decide to add fog lamps. Those fog lamps need to be protected as well, so we need to design that circuit based on the current rating or amperage draw of those fog lamps. And then we need to put in a circuit protection device that is just large enough that it won't blow under normal operations, but if we short out that circuit and have a problem with that circuit, that circuit protection device will open, making sure that the vehicle wiring doesn't burn, causing a fire, causing the vehicle to burn down, causing damage to the switch, and all sorts of other components. Some current protection devices are designed to open more slowly or more quickly than others to permit an inrush current. So inrush current is that peak current. So a lot of devices you're going to see, they say, you know, peak amperage output or peak amperage, peak draw. So when you first turn on a light, it may not take as much current, or it may take more current. So when you turn on a motor, a slow turning motor draws more current. We're combating that counter EMF and things like that. So they draw more current when they're moving slowly. As they get up to speed, they take less current. But if our circuit protection device is set too low or designed in too low, it'll pop every time we turn our motor on, and we don't want that. So we're going to let that motor start to turn and the current draw to come down, and then that's the normal level that we're going to protect. However, if you were to have a long-term short over a long period of time, it would heat up and melt that circuit. So it's just a little bit more robust if you're designing an inrush current circuit, or sometimes you want a quick blow because you don't want to allow any inrush current, or you don't want to allow even for a longer period of time to have excessive current on that circuit. So common causes of excessive current flow in a circuit are excess current draw devices or a short to ground. So we can add components to a system, and it will, depending on the circuit type, you will start to draw more electricity. And the more electricity you draw, the more current you draw, the warmer the wire, the warmer the circuit, and it's going to heat up that circuit protection device and blow it or pop it, and so that's a problem. Okay, the last part here. Always replace a circuit protection device or fuse or circuit breaker with the OEM recommended rating. So let's say I intended to add a circuit to the vehicle. I'm going to need to go redesign that circuit, make sure that I'm designing it to the weakest link so that I don't burn anything up. If, let's say, I come up to my vehicle and my lighter doesn't work, okay, my lighter socket or my power point socket in the vehicle doesn't work, and I look in the manual, it says I need a 10 amp fuse, and so I put in a 10 amp fuse and it blows right away. Well, it blew right away because there's too much current being drawn on that circuit. Now I could go and grab a 15, and it may not pop it, or it may take longer to pop that circuit. Okay, and so I said, okay, well, I'm getting close, so I put in a 15 and it didn't blow right away, so I'll put in a 30. Okay, now what's happening behind the scenes is there's some sort of a circuit fault, most likely a short, and most likely that short is heating up the wire behind the scenes, in your dash, in the firewall, or behind the firewall. You're having a problem, and what the term we like to use in the automotive and diesel industry is you're about to let the smoke out. Okay, once you let the smoke out of something, it's very, very difficult, if not impossible, to put the smoke back in. What are you going to do? Grab the smoke and try to blow it back in there? Okay, so that's kind of a joking term, but that's what we say. We let the smoke out of it. Well, once you let the smoke out of it, it's very difficult to put the smoke back in, if not impossible. And so you're going to end up needing to replace those wires, replace that component that you just smoked. You never know where you're going to find that weakest link, and that weakest link could be in a very, very inconvenient location to repair, or it could be a very, very expensive component. So we don't want to replace standard circuit protection devices from the OEM with a higher rated circuit protection device. If we do any of that kind of stuff, we have to know exactly what we're doing, and we have to design the circuit to match. All right, typical automotive fuses. So here we have your ATC blade style fuse. Okay, then you have your glass fuse. Then you've got your fuse element top here. So here's that same blade style fuse from the top, and we usually have a couple of pins right here, and that's this portion of the blade right here. And we are able to put a test light on there or an ohm meter, and we're able to test this fuse to see if it's blown. Same thing with this style, same thing, maxi fuse. So we have mini fuses, we have the auto fuse, the ATC, and then we have the maxi fuses. And again, the mini fuses blow pretty fast, the auto fuses last a little longer, the maxi fuses, yet again, a little bit longer. But also, they are made to carry up to 150 amps, 60 amps, 70 amps. So they're a bigger fuse, taking a lot more current. All right, circuit breakers. So circuit breakers are another form of circuit protection device. Circuit breakers are a form of CPD. The circuit breakers have a thin bimetal strip that when it is heated, it bends or snaps and opens the circuit. An open circuit breaker is considered tripped. So we've tripped the breaker. That's another term you may hear. When a circuit breaker cools, it resets. Okay? Not all of them reset automatically. So you do have circuit breakers that do reset. Now, if you think of if you live in a fairly modern home, you've got circuit breakers in your garage or in your house that when they trip, they open the breaker and you slide the contact shut again. That is a manual style breaker. Now, there are 3 classifications of breakers that we use in our diesel applications. We have type 1, type 2, and type 3, and they all have different resetting characteristics. So those characteristics would be type 1 circuit breakers automatically reset after they cool down. These are a very popular type if you have an intermittent failure and the failure goes away. So if you have a wire that's just chafing a little bit and the circuit heats up and it blows the circuit breaker, it trips the circuit breaker, then it will, when it cools down, when the chafe is not active anymore or whatever, it'll reset. So these are nice for safety and things like that. Then we have a type 2 circuit breaker. These automatically reset after the cause of the excess current is no longer present. So different from the cool down, these actually can still sense if the problem is still there versus just automatically resetting, waiting to heat up again and opening. And then our third type is a circuit breaker that is manually reset after the excess current draw is no longer present and the bimetal strip cools. So providing that the circuit breaker has had time to cool down, you could go in and reset this. Now, if the problem's still there, it's going to heat up and pop again. So we usually use some sort of verification process to make sure that we're not still over amperage on that circuit. However, all of these have their benefits and drawbacks. Okay, so we use them all differently. This type 3 is very popular in international. They like their manual circuit breakers. Now, the nice part about this is that it does take a technician or a mechanic or someone who can read a circuit map to find that circuit breaker, be able to analyze whether or not it's tripped or not, and reset it. So it is going to probably break. It's going to disable that feature. It could be your headlights, could be whatever. It's going to actually disable that until someone takes a manual look at it. We also have circuit breakers that automatically reset. So if you're using your blower motor too much and it heats up the circuit, it'll trip the circuit and then reset. So they all have their place, and you'll see them in different applications. All right, so here's that type 1, type 2, type 3. Again, so here's a type 1. It just heats up, the metal gets hot, expands, and opens the contacts. This A here is the type 3. This is the manual resetting. So when the current gets too hot, it just pops the reset button, and you have to manually reset it. Okay. Then you have this type 2 style here. Now you'll see that there's some little heater wires here. Now those heater wires can keep the circuit connected in a sense. So it senses whether or not that current is still too hot or too high, because it's going to keep this bar a little too hot to actually close. And that's going to tell us whether or not the problem is still there, whether or not the problem is solved. Okay, so let's talk about the application of circuit protection devices. So our circuit protection device is going to protect the wires in our system. So one fuse protecting several circuits, as we have in figure 4-53. So one fuse is going to control the power side, the high side. So let's introduce that concept. So we talk about our positive voltage being power and our negative side being ground. or high and low, and we'll talk a little bit why we call it high and low here in a minute. So our power side of the circuit is fused, and it's going to control all this. Then you can have we're still on the power side of our component, but we have a fuse for each parallel branch, each component on that circuit. So we'll talk a little bit about that. All right, typical truck circuit protection device layout. So we have our positive here. We have one 150 amp circuit breaker, and this one circuit protection device is going to make sure that if anything over here has a major short, that all of it's going to be protected, nothing's going to burn up. And then from there we have each leg, so we can only, on this side of the circuit now, from this 150 amp, that means that we cannot go over 150 amps on this downstream portion here. If we do, we will blow this fuse. So we have to keep this below 150. So we have our 30 amp, our 20 amp, and our 20 amp. So last time I checked, that was 70 amps. So we're well below this 150, so we shouldn't have a problem there. But depending on what's downstream from this arrow here, we could have a problem. But we have a 30 amp here, so now everything from this point down to the ground can't exceed 30 amps. Everything from here down can't exceed 20, and so obviously we have three different, components or loads. And then here we have a circuit breaker for 20 amps, and we can't go over 20 amps on that one, but it is a CB1, so if we go back to our reading there, this is a resettable circuit breaker. All right, an open circuit. We're talking about terminology for wiring problems. An open circuit is a circuit with high or infinite circuit resistance. So an open circuit which results in reduced or interrupted current flow in a circuit. So we think about open circuits as a break. Okay? What if our circuit is not broken, but it is so corroded, or instead of having a big connection, we have a small connection. So we've cut through our wires or have a lot of high resistance due to corrosion. At a certain point, like 10,000 ohms, we consider the circuit open. Even though you could get continuity with an ohm meter, you could check with your meter and have a circuit connected there. But what we assume at that point, if you use Ohm's law and you plug in, 12 volts with 10,000 ohms, you're getting milliamps of flow, and you really can't do anything with milliamps. So we consider that at some point we consider a high resistance circuit to also be open. Okay, so we'll talk a little bit about that in lab too, or we'll actually talk a lot about that in lab. All right, a short to ground occurs when the conductor in a circuit has an unwanted contact with ground. So some shorts to ground don't matter. Some shorts to ground, let's say before the load, so our voltage hasn't flowed through our load yet, that's a short to ground that we don't want. That's a short to ground that's keeping our load from actually working, and we don't want that. Short to battery positive occurs when the conductor in a circuit has an unwanted contact with the positive voltage source. Again, a short to, and so we'll call these short to low, short to high, short to power, short to ground, short to battery. So there's some synonymous terms we'll use there. And then a wire-to-wire short occurs when the conductor in a circuit has an unwanted contact with another wire. And this wire-to-wire short could be a short to ground or a short to battery. Okay, so it could be high or low, could be could be two positive wires, two ground wires. But what happens is oftentimes we're powering a circuit that we don't want to power, or we're grounding a circuit that we don't want to ground at that time. So you can have an issue there. If nothing else, you may have a wired to wire short with open insulation, and you're getting corrosion and other things into that wire. All right, types of wire defects. So let's talk about this. So we have 12 volts dropped across an open circuit. So here we just are getting way too much resistance. Then in B down here, we have a short to ground. So here's our positive. Okay, we're coming from the battery, and we short to ground before our load. So there's really nothing happening at our load because there's very little voltage to actually power our load. And if we had a circuit protection device in here, we may actually pop that circuit protection device. So let's go here to C, which is a short to battery positive. So we're coming up with our battery positive, but we're shorted before the switch. So now our switch doesn't control our load. Our load is on at all times, even though the switch is open or closed. So that can always be a fun one. And then D is our wire-to-wire short. So where two wires have crossed paths, this switch is closed. So it's actually controlling this circuit incidentally instead of on purpose. And so when we open and close this switch, it makes little to no effect on the circuit, and so then we have a problem. All right, basic electrical diagnostics procedures and flowcharts. Okay, this is that paint by numbers diagnostic that I'm going to teach you quite a bit over time. So we're going to start at the beginning here. Okay, we're going to verify our concern. Okay, if we can verify our concern, we're going to go down here to step 2. If we can't verify our concern, let's say the customer comes in and says, hey, my headlights don't work, and I go to look at them and my headlamps are in fact working, then obviously I have a problem. So I'm going to come down here and we're going to re-examine the complaint, and we're going to say, okay, well, ma'am or sir, what's going on with your headlights? When did they stop working? When did they start working? And gather some more information, and maybe they'll find out that, oh, it's my fog lamps. Did I say headlamps? I meant fog lamps. And so then we'll re-examine the concern. So we're going to verify our concern. If we can verify it, we do have that problem. Then we are going to perform preliminary checks. Preliminary checks really consist of function checks. Okay, does the switch work like the switch is supposed to? It feels good. Everything's fine. Okay, we're going to check the component itself, that it's plugged in. We're going to check some things like that. We're going to check the fuse, just normal, just little quick checks, little things that we can, least intrusive method, we can just get in and check them real quick. Maybe we'll trip across the problem during an inspection. Then we're going to refer to our service information. We're going to go to, like with Ford, you'd go to Oasis and you type in a symptom, concern, or a code, and it's going to tell you, oh yeah, every 2000 Focus has a problem with the high beam switch, the multifunction switch. We need to go ahead and replace that. If you find this concern, do this test and that test, and then replace the multifunction switch. Then you're going to find different types of information. Could be a recall for the problem that you're having. Then we're going to perform system checks. Maybe we're going to pull codes. Maybe we're going to do certain diagnostics or certain checks. Then we're going to find the problem and isolate it so that we can find out if, maybe you'll find out that, yeah, there's a problem with my headlights, but you know what? There's also a problem with my taillights or my turn signals. The problem could be more widespread than the customer noticed. So we're going to isolate that problem and try to diagnose it. Then once the problem's isolated, we're going to repair and verify and then implement preventative measures. So whatever caused that in the first place, maybe it was a bad ground, maybe it was poorly insulated wire, maybe we need to put an extra zip tie in or put some extra convolute over it. And then really what's in this process, we want to find the root cause of the problem. And so when we talk about implementing preventative measures, maybe that's the root cause of the problem was the lack of insulation that actually caused the rubbing of the wire. So if we just replace the wire and it rubs through again, we didn't actually fix it, we just fixed the symptom. The problem, the root cause, will come back. So we want to think about those types of things while we're diagnosing. All right, common wiring diagram schematic symbols. I'm going to let you read through this one and kind of start to build your language up. Okay, and this is like that key in a map. So this is, I'm going to let you read through this. We're going to go through this in lab quite a bit, so I'm not going to go through this and you know, beat a dead horse. All right, fuse wiring diagram for heated mirrors. So here's our heated mirror elements. Here's our backup lights. And as you can see, this is what a typical truck diagram may look like. And so we have 12 volts at the top and we have grounds at the bottom. That is where that term high and low comes from. So if the problem's high up in the schematic and low in the schematic, that's where that term comes from. So here we have our 12 volts coming from the ignition. We hit our 5 amp fuse. I'm sorry, F5 20 amp fuse. And we come down here and then we have our switches, right? So this is the high side, everything on top of the switch. Everything below the switch is our low side. So if I were to grab a meter and check right here, I would have a ground. If I grabbed my meter or my power probe and I checked here, I would have 12 volts positive versus 12 volts negative. Okay, so we're going to talk about circuit diagrams and power probes. I love the power probe. I teach the power probe. You're going to buy one in my program, and you're going to love it, and you're going to thank me later. All right, using peak, hold, defined, and intermittent short. I'm not going to go through this right this second. We'll go over this in lab. But there's some features in your meter that are going to allow you to set your meter to a certain spot and then check for intermittent problems. And look for a peak voltage or a peak amperage problem, and you'll be able to find the problem. And you can read through this section in your book. I really encourage you to do that, but I'm not going to go through it today. I think it's a little bit too much information for a visual presentation. All right, test lights. So a test light is basically a clamp that we put to ground or to positive, and a wire that connects with a light bulb in the middle. And so we can look for powers, we can look for grounds, just depending on where we put this clamp. But in this case, the clamp is on our ground. It's on our chassis ground. And we are checking for power at this connector. And when we find power, we will have a path from power through the light bulb to ground. And the light bulb will light up. And if we don't have a light bulb that's lighting up, we either didn't attach the ground properly, or we didn't touch the tip to the connector properly, or we don't have any voltage flowing through here, or we don't have any ground. And so you'll figure this out. And again, we're going to use these tools quite a bit. All right, normal voltage readings. So can our voltage be higher than our battery? Not usually. It's very rare for that to ever happen. Now, if we measure our battery and it gets 12.6, that's a good battery. And then we turn our car on and we go to go check something and we get 14 volts. Well, that's shocking. It's more than our battery. Well, typically if we go back to our battery, we're going to have 14 volts at our battery as well, because that alternator is sending that power there. So yes, you can have more voltage. You can have more than 12 volts in a 12 volt system, because you need those extra couple of volts to actually charge the battery. All right, so as you're looking at this, we kind of talked about normal voltage readings. With our normal voltage, we're going to have 12 volts right here, and then we're going to have 0 volts going across. So typically what happens when you go from power at the top to ground at the bottom, by the time you get to the bottom, you should have no voltage left over. All of the loads have used all of the voltage. You'll have like 0.01 volts. Just enough pressure to get back to ground, and that's it. So if you think of voltage as pressure, that's what's happening, is that someone's pushing and you just have just enough to get back to where you started, or just enough to get to your destination, which would be the ground. All right, so again, I'm going to let you read through this summary. I encourage that you do so. Read through this summary. You can pause it, because I'm going to click through this pretty quickly, so you can pause it and read through the summary. Make sure that you understand the concepts that were covered in the chapter. Make sure that you are understanding what happened in this chapter. If you don't understand, please email me at rush@klamathcc.edu. We can talk about it, or you can call me on my office number. It's 1-541-880-2326. And we can talk about this. Or save your questions up for lab, and I'll talk to you during lab.